said I was going to do today is basically just go through a number of the instructions using the board and kind of go through how these instructions work on the processor. So in order to do this, of course, I need the board. That's why I didn't do this yesterday, was the lab tech wasn't in and I didn't bring a board with me, so that's there. And we may or may not be here for very long tonight or today, because I'm just going to go through a number of the instructions and how this would work. And the next week's lab will be for you to repeat the same type of activities. That there. So let me go ahead and bring up the software, and I'm going to bring up the code that I was looking at yesterday, and I'm going to just edit that file right there as soon as I find the software here. Oh, I don't want that. Up there. Close. I don't. All right. We will ignore you. Don't you love programs that won't let you shut them? We need the internet, but you can't shut us off because we need the internet. So, all right. So I'm going to go ahead and just bring up the most recent project which was load recent project file. Let's just go ahead and bring up our Blinky that we did yesterday. And I'm just going to just use this so that I don't have to retype everything right here. So I'm going to basically stop my code. Actually, what I'm going to do is I'm going to comment out all these lines that deal with the that there. We'll come back and look at those later, but I'm just going to comment them out there, and so that I can sorry. Yeah, well, unfortunately, I have two classes back to back, so I had to plug my computer in, so I moved the table this way. I could move it back to that side, but I'm just going to go ahead and just stay here, right there. You're not going to sleep? Okay, well, I mean, if you sleep, I'll just pick on you. That's there. So, I know that some of this stuff is kind of boring, that there. It is easy to want to fall asleep during it, but at least this time of the day, you should be awake, right? At 10 o'clock. The 8 o'clock class, I have a class at 8 o'clock. They seem to struggle for that first half hour or so. And then any class, say, that starts at 2 or 3 is right after lunch, and forget it. That's nap time for there. So, and actually, you get to 5 o'clock, some people are still. That's usually my nap time. My wife says you're not supposed to nap between Asar and Marguerite, but that's my favorite nap time. Forget it. That there. 5 o'clock, I'm taking a good nap till about 6:15 or so. That's there. So evidently, so again, I'm going to go ahead and plug the board in, and I'm just going to go through and I'm going to run this code and write some instructions and just kind of go through and show what's happening. Now, right now, I commented out all the code except for, I went ahead and left in the green LED so I could turn it on and off so that you can see on the board that I'm actually executing the code on the board. So right now, I just called it blink. I'm going to go ahead and leave the watchdog timer disconnected right there. So this code right here is really just so that I can use the LED and disable the watchdog timer right there. So I'm going to go ahead and start writing my code here for my example here. So I'm just going to, for example, let's move into A, and upper or lowercase doesn't matter before you start asking the question. I typically use uppercase for instructions and lowercase for register names, but I'm going to put the number 35 in there. I'm going to move into R0A. I'm going to move into R1, the number 95. I'm going to move into B, R1, right there. So just a simple set of instructions that does absolutely nothing right there. Right there. Capitals don't matter. Upper or lowercase doesn't matter whether that's there. So I use R1, upper or lowercase, that there. Some languages such as C, it does matter. If you're programming this processor in C, upper or lowercase has to match. Here it doesn't. So I'm just going to go ahead and compile this. And remember, this is the assemble, this is the build, which does the linking. This does all three, or both at the same time. So that's there. And assuming I didn't make any mistakes, it will come up here, and those that are in the front probably see on the bottom, it says link, locate, run, complete, 0 errors. If I go a little further up in here, you'll see where it does the assembly. So you can see that it runs two different programs. It runs the assembler, and then it runs the linker. If I just do this one here, it only runs the assembler. If I just do this one here, it only runs the linker. If I run this one, it just does both. I'm a lazy person. I just hit one button, it does both. The only problem is if you've got an error, is you have to go back and find the error right there. Because this one here, for example, if I said R9, which there is no R9, if I run this, it'll come up with a IO path not found. That error means absolutely nothing. You got to go farther up here. This is one error, undefined. That there's it's on line 45, and it says error A45 and 249, undefined symbol pass 2, and you see this 3 asterisks underneath the R9. That tells me that that's where the error is. So I'm going to just go ahead and change that back to R0 and run it again right there. So once we have this, I'm just repeating the process we did last time. I plugged the board in, I connected to the board. Now in this case, it connected cleanly because the download came on right there. If there was a problem, for example, let me disconnect it, and the board was disconnected, for example, it will give me an error right there. And I say okay, and notice that that's not on. So if everything's good and the driver is there, we discovered, some of us in the first lab session, that those computers, the drivers are not necessarily there when you first turn them on. You got to wait 10, 15 minutes for the drivers to show up. That's just the way that lab is set up. That's there. So I'm going to go ahead and reconnect and download. Now, I download the code. I don't want to run this code because this code does nothing right there. All it's going to do is just it just hangs there. I have no idea what it's doing. That there. If I hit that there, it's hung up. So we come over here, we reset everything there. Right there. What we want to do is we want to put breakpoints in so we can see what's happening. And our breakpoints are important right here. This sets a breakpoint there. So that's going to stop the code when I reach that point right there. Now what's important here, and it's hard to show with these projectors because of the resolution of the projectors that there, but I'm going to go ahead and do it, and we're going to probably have to move around the screen. When you run this in the lab, let me put my glasses on that there so I can see the people see who's sleeping here. So I know who to throw something at. That there. You said you weren't going to sleep, so that there. No, actually, I'm one of these people that put their glasses up and down all the time. That there. I hate doing this with the bifocals. Some of you will get old and wear bifocals at some point in your life, right? That there. So, okay, what we want to do here is we want to look at the registers and the processor. That there. So if we go under View, we have something called the debug windows right there. Now I'm going to turn off the output window, which is down below. So under View, you can turn on the output window, you can turn on the project window, you can turn on the toolbars, which toolbars you want, close, right there. I'm going to turn everything off right there. Turn off the status bar and the workbook mode. And the reason I do that is simply because I want to get as much on the screen as possible. When you're in the lab, you don't necessarily. So under View Debug Window, I want to look at under SFRs, Special Function Registers. Let's look at the compiler. Now this shows me the accumulator and B. It also shows me my watchdog timer information there. It shows me my program counter, my stack pointer, my data pointer, all that program status word, all that is shown inside the processor. The other thing we want to do is we want to look at the registers. So they're shown on the bottom right there. So we can see our registers there. We can also view under Special Function Registers. I'm not going to show them today, use it today, but we can also put our ports here, show our various ports right here. So everything in the processor we can see in this window right there. So now when I go through and I run this right here, it stops at my breakpoint right there. So I didn't see it set up at there, and I'm going to go through and I'm going to resize this right here, because really we could turn off the ports there, but I'm going to go ahead and leave them on to show that, you know, when I set that there. So the first thing I did really, let me reset this again, and let me put the breakpoint right here, and run this again, and we stop there. If I single step through here, and this is where you're going to see things happening in your code, is this command here is single step. Now, if you have an F11 key on your keyboard, which I do, but I have to hit 2 keys to get it, I'm just going to hit the step button right there. If I do this, it's going to execute that command. Now, if it changed something in here, I would see it change right there. So I execute the next command right there. And I see at this point that P1 mode out changed to 0, 1 right there. You see where it's red? That tells me that changed during that operation. So that red there. So the next one should be clear LED right there. So I set this right here, and port 1 changed. And the LED turned on right there. As it turns out, when you clear it, it turns the LED on. When you set it, it turns it off right there. So I single step here again, right there. Now A now should contain the number 35. Now I screwed up, which is not unusual. You've watched me make many mistakes. I didn't put the H after that. There. So it shows up as 23 here. So let me go ahead and put the H's in there so it looks right, and insert that over again to show in hex, because the answers are everything is in hex. So let's have the code match. Is that me or somebody else dropped something back there? Oh. Okay, that was me. So let me recompile. Now when you recompile it, the breakpoints are lost. So let's go ahead and or you got to download it again, and then the breakpoints are lost. So okay, so I go ahead and run it, and we'll see as I go through and I single step through some of these things change there, right there. Also notice that the program counter changes every time I single step, right there. And then the LED is off. I run this instruction, the LED came on. And also down here on the ports, right here, you saw that changed to FA right there. So I set that there. I single step through again. 35 should have shown up in there. Did I recompile that? In A, excuse me, I should be looking at A. See, 35 has showed up in A here, right there. I do the next step. R0 should now show 35. So these are I'm looking inside the processor. I can't do this without the processor. Now I'm going to move 95 into R1. So R1 now contains 95. And then I'm going to move that into B. right there. And what happened here? My address now shows up there. Right there. I want to close it. I don't know why that window opened up there. But now I moved R1 into B. I single step it again. I move R right there. Oh, the reason is because I'm out of code. That's why that's opened up there. So to solve this problem, I'm going to put in an instruction here called, I'm just going to say start right there and put in no op right there. And at the end of my code right here, I'm going to put a long jump to start right there, so that you can see that I will jump back. Yes. What's that? No op. In other words, do nothing. It's just no operation. Yeah, in other words, it's just a space holder right there. So no op is just no operation. That there. So it's what you do when you take a nap. Right there. So again, we recompile it and we re-download it. And I'm just going to go ahead and put my breakpoint here. Put my breakpoint right there. So it's just going to go through here, right here, and then as I run it, it stops at start. The breakpoint, that just tells the debug hardware to stop the code at this point, so that you can see what's happening. See, it puts that little red dot there, and you use a stop sign. In other words, stop at that point, right there. You put it, and it's going to stop before the instruction, before it executes that instruction. So right now, it has not executed the no op. If I hit the step point, it will execute one instruction, and the no op, and you can see over here actually the instructions that are being executed there. Right there, no op, and this tells me what the instructions is right there. So this is showing me in memory where I'm at right there, right here. So I shut that window off a few minutes ago because it's really the same information. But what's different over here in this window, let me just move this over to where we can see a little bit more of this window, is that this shows the address right here. And see, and that's the same as the program counter right there. That shows the address where I'm at in memory. Right there. This shows the opcode is 74 for move into A, and then this is the data that I'm moving 35. So this 7435 is the same thing as move A number 35 right there. So this is how, so we're seeing the code execute at this point right here, and then here are our various windows. Again, when you're in the lab, you can see more of this on the screen, right there. But a lot of this is not necessarily showing the instructions, but more of it is how to use the debugging tools, right there. So, because when you're writing code and it doesn't work right, it's good to be able to stop and see what's happening there. Now, Visual Studio does the same thing. Did you ever learn how to use the debugging tools in Visual Studio? Because in Visual Studio, you can set breakpoints and watch points and things like that too. So Visual Studio, for when you got C code that doesn't work, you could do the same kind of thing. It's not as important in Visual Studio because you can put printf statements in there and see what's happening there. You can print out various variables and things like that. But here, we don't have a printf statement. I don't have a serial port tied to this. So I can't see what these variables are equal to. I can't print them out. So the only way that I can do this is right here. Now, so now I just go through and I single step. Now I also have a multiple step where it's just going to keep stepping right there. And you can see it goes through and it shows the code going through executing right there. And then I can stop it there. It's more useful just single step than it is a multiple step, but sometimes you might want to have it step through some code, see what's being executed as it's being executed. That there. So let me just step through this again so you can see, and I'm going to make this program a little bit longer, a little bit more complex. I'm going to add more instructions to it, put in some loops, and so we can see how these instructions work right there. So right now all I've covered is just the move instruction. So no op does nothing. Now I'm going to move 35 into A, right there, and 35 now. Notice it didn't change. I keep hearing, oh, okay, that's there. You notice that 35 didn't change because I hadn't changed it. It's still 35 from the last time. So we probably ought to change some of these so that we see them change every time. So, but we'll just go through this again. We step through the next one. I move into R0. Again, nothing's changing in R0 because it hasn't changed right there. So what I'm going to do actually, I'm going to go through and change this code to clear out a bunch of stuff. That way we can see it change every time. So let's just do a move A number 00, move B number 00, move R0A, move R1A, right there. So, and the reason I did that is just so that we see it change every time. Right there. So again, we put our breakpoint in right here. Insert breakpoint, that there, so that it stops. So when I hit the green arrow, it will run till that point and just stop, is what it does. That's what the breakpoint does. So then I execute one instruction right here. Now here we're not going to see much change because it's already 35. So I'm going to go through and we're going to see here we're going to move R1. Now I move 0 to A. I see A is changed to 0, 0. I do the next instruction. B changed to 0, 0. I do the next instruction. You know, R0 is that there and that there. And now I jump back to start, right there. And now I see 35 goes into A. I see that 95 goes into, or no, A goes to R0. 95 goes into R1, right there. And 95 goes into B, right there. And then we do that there. So now let's go ahead, let's put in an add instruction right there. So we can see this thing add. So let's just go ahead and do an add A, B, right there. So again, we're just going to turn on the LED so that you see that it's actually being executed on the board. That's the only reason I turn on the LED, just so that you proof that it's being run on the board. No op does nothing. I move 35 into A. There's my 35. I move A to R0. I move 95 to R1. I move R1 to the other. And now I'm going to add A and B, which is 35 and 95. And A now contains CA. So I did the addition right there. And notice that the program status word didn't change. So now I'm going to change this addition to where I get a carry out right there. So we can see there that if I run this here, I clear and what happened there? Did I, oh my, why, oh, okay, I'm sorry folks, I put the breakpoint in the wrong place. So every time I run through this, it'll stop at the start right there. So, okay, now I'm going to change my code. Instead of 95, I'm going to put, or 35, I'm going to put F5 there. Now remember that I got to put a 0 before the F, right? So if I leave the 0 out, it'll give me an error. So, and I'll just do that just so that you see the error. And If I tried to download it, it's going to tell me file not found. I turned off the output window right there where it shows that there's an error right there. Right there, see where it doesn't like that there. So I put the 0 in and I recompile it there. So this time it compiled cleanly with that there. So I can now download it. Now the only thing I'm going to show this time is when I do the addition, I'm adding together, in this particular case, I'm adding I'm in hex. I'm adding, what did I say? What did I have here? F5 and 95. So F5 plus 95, the answer is 8A. That there. Well, obviously that's not right because we had a carry out is what we had. That there. So when I run this code, this time, right there, and I single step through this right here. Now, let me just stop at this point. When I single step through this right here, and I'm going to do the add right here, notice that A contains 8A, but also notice at above it, the status word changed. Now the status word contains the carry flag. Now I'm not going to go into where the carry flag is, but the carry flag is there, right there. So when we had the carry out, we had a carry. When we did the add, we had a carry out, and it changed the carry flag. So if I was to do another add with carry, the carry flag would take into place. So if I want to, for example, I want to add two 16-bit numbers, how would I do that? So I'm going to go through a little project here where I'm going to add two 16-bit numbers and show you how you would have to do that. That there. And actually, that's one of the labs that's assigned later. Let me find my... Did I put my pen up here, or did I... There's a still down. All right, it's not there. Did I throw it in here? I had it last hour, so it's either... I need my pen. We don't see a pen up here, do we, anywhere? No one sees it? Nope. So it's thrown in here. It's in the bottom of this thing somewhere. It feels just like, looks just like this here. Okay. So what we want to do here is I want to add the numbers 23, F5, 95, 27, for example. I want to add those two numbers together. Now I can't add them together directly because they're 16-bit numbers. So I have to add these two together first, store the result, and I'm just going to go ahead and store the result. And we know that this is 8A, right? And so this one here is going to be 11, 10, so that's going to be B, and this is going to be 4B, 8A, is what the right answer is going to be. So I'm going to add these two together first, and I'm going to store this result in R0 and store this result in R1 when I'm done, right there. So we're just going to write that there. So we'll remember 23, 27. Okay. So again, all I'm going to do here is I'm going to shorten this here a little bit right here, and I'm going to move into A there. I'm going to move into B. 95, right? I'm going to add AB, and I'm going to move that to R0. I'm going to move into A, now 27, hex. Move into B, 23 hex. I think those are the right ones. 23, 27. 23, 27. That's there. There. Now I'm going to do an add AB. Now that's going to give me and move A to R1. Now this is going to give me the wrong answer. Right there. Right there. That's going to give me the wrong answer. And the reason it's going to give me the wrong answer is because I didn't take into account the carry. So if I go through and I compile this, download it, up, it doesn't like something there. What doesn't it like? Add, move. Oh, hold on here. This is not right here. Move to R1A right there. Right there. There. Well, what doesn't it like there? Oh, right here. Move. Move. I didn't finish this instruction. Right there. Move A into R0. Okay. That there. I could have pulled up the output window and found where the error was. I just looked for it without opening the window there. So go ahead and put the start there. So now I'm just going to go through the add process right here, step by step. Right there. Move. So accumulator contains F5. B now contains 95. So I do the add, and it contains 8A, which is what we would expect. So we move that to R0, and now it contains 8A. And then we move 27 to there, and we move 23. We add, and now that's 4A. That's wrong, right? And the reason it's wrong is because we didn't take into account. Because 27 plus 23 is going to be, the right answer is 4A. But we're adding two 16-bit numbers, then we go ahead and store that there. So I'm going to change this second one to an add with carry, right there. That's the reason we need the add with carry. Now when I run this through, right there. Now when I run this, again, I'm just going to single step through it. I'm not going to go through everything as I single step through it. You've heard me comment on everything already that there. So we just single step through there. Our 95 is an A. Our F5 we add there. There's our 8A. We move that to R0. There. Now we move 27 and we move 23. Now when we add, notice we got 4B. So we need the add with carry to take into consideration the carry function right there. So and then we go ahead and there's our right result, 4B, 8A. That is the right answer we get. So that's why we need the add with carry right there. So now let me go through some of that there. And let's modify this code where we just run it 3 times, for example, right there. So I'm going to use R2, for example, as a counter right there. So at the beginning here, and I'm just going to put another command here called loop right there, and I'm going to put another no-op here. No ops are commonly used as loop starters right there. Right there. No op. Now, before I do this no op right here, I want to move into R2 the number 5, say. Right there. I'm just going to move the number 5 there. And the reason I'm moving the number 5 there is that I want to show that I'm going to go through this loop 5 different times. At the end here, right here, I'm going to do a decrement jump not 0 R2 comma loop right there. So I've added a couple lines here, and all I want to do is show how we do a loop 5 times right there. So we're going to go through this 5 different times here. So let's compile it. Right there, and I didn't add any mistakes. Let's go ahead and put our breakpoint in here and kind of walk through this one at a time, right there. And so I'm going to go ahead and run it to the breakpoint. So here at this point, the first thing we do is we moved into R2 the number 5. We'll come back and we'll look at that again later. So we're going to just go through and single step through our code, and I'm just going to just walk through it real quick. And then I'm going to execute this command, decrement and jump not 0 back to loop. Notice it goes to loop, and R2 is equal to 4 now. Yeah, see, R4 now is equal to 2. Because it was 5. I moved 5 to it initially, but this command here, right here, subtracted 1 from R2. It was not 0, so we jump back to the label loop right there. We go through and we single step through this again. Right there. And again, I'm ignoring everything else going on here. We execute that command again. Notice that R3 is now equal to 3. So we go through it again. So now it's going to go to 2. We go through it again. Now it's going to be 1. We go through it again, right here. And now I subtract 1. And notice it did not go to loop. It skipped to the next command. The next command is ljump start. It goes back to the beginning. So now I've generated a way that I could do something 4 or 5 times right there. So now one of the things we might do, I'm not going to do it today because I'm trying to keep the amount of material I'm covering to a reasonable amount that you're going to remember that there. But what we could do next is we could set up a series of numbers in a bunch of memory locations. We could add them together and increment a counter right there. So what we could that there. Now, how do we move the memory right there? So again, we've looked at moving things in and out of the register. We looked at how we add. We looked at how we set up loops. Now, how do we use memory? Using memory is very easy. Let's say, for example, I want to preload some information at the beginning of my program into 5 memory locations. Right there. So, up here at start, and I'm just going to make these up here. And I don't know, move to 30, the number 10. Move to 31, the number 11. And we'll use 20. Move 32, the number 30 hex. Move 33, the number 40 hex. Right there. That's good enough there. So what we're going to look at here is I'm going to recompile this, and you notice that download it right there, it flashed right there. Now, if you look at these instructions, there's nothing in front of them, these numbers, and actually I made a mistake here. These should all have H's at them. Right there. Let me recompile and re-download it. I forgot the H's. That there. Which I tend to forget once in a while. So now let's go ahead and put my breakpoint in here. Reset this. Put in my breakpoint here. Now, when I single step run this, and I single step through here, I don't see anything happening here because I need to go back here and RAM right here. Now, again, I'm going to close this window. We're going to ignore this window here, and I'm going to ignore all these windows here for right now. And this is the RAM in here. This is our RAM. And I want to kind of go through this. And I want you to see some interesting things that happen with the RAM as I go through this program. The first command is I move 30, or the number 10, to location 30, right there. Now, it didn't change because I ran it first, right there. So right there, and I forgot the H here, so right there. Let me change all these so that we can see them change since I screwed up here. The reason I did that was simply because I accidentally hit the run button and they all changed earlier. So I put the breakpoint in. So, if I single step through here, you should see on the next command location 30, which is 30. This is location 30, 31, 32, 33, 34. So you see that now contains 11. I execute my next instruction, that's going to contain 21. I execute my next instruction, it contains 31. I execute my next instruction, that contains 41. So you can see that this is the data memory right there, is what we're looking at right there. We're looking at the data memory. So we're writing the data memory now and not the registers. Now, the next one is a little bit interesting here, is notice here that this 5 changed right there. You know, and I moved into R2 the number 5. Something I have not talked about, but when we look at memory right there, and we look at, this is our data memory right here. Data memory. Location 00 is the same as R0 in bank 0. Right there. R1, R2. So we put the number 5 there. So what we've done here, when we move something to our registers, we're actually changing RAM. It's shared right there. So bank locations 0 through 7 are the same as R0 and R7. That's why we don't want to use them as RAM. And that goes all the way up to 1F right there. So we don't want to use locations 0 through 1F because those are reserved for our 4 banks right there. Now, if I change this, theoretically, it didn't work last time. Well, let's change that to a 1. That's going to be bank 1 right there. And I go through and I run the same code right there, right here, right here, and we're going to see that we're moving our, there, that doesn't change. Now when we move 5 to here, and it didn't change, it's not working right. So that's a little bug that I've got to figure out why it's not. It should have changed to bank 1, which would have been down here in memory later, but it didn't change. It's still using bank 0 right there. And it could be that this processor doesn't have a bank 1 and 2. It may only have bank 0 right there. So, but regardless, you can see that our 5s changes. Everything else stays pretty much the same right there. So I think that's really all the instructions I want to go through today in detail. I don't want to get into indirect addressing today. Today was kind of meant as kind of a short day to kind of demonstrate the types of things I'm going to have you do in the lab on Monday, right there. So, but there's using this debugger is very, very important when you're doing real work, because this is where things happen there. Before I stop here, though, let me close this project. Let's close project. Let me close the project right there. Let me close everything out here. And let me open up this is the C version of that code right there. That there, and this uses the timer and everything else. This is the C version. That there. And again, it does very similar things there, but I just want to kind of show you what happens. Let me exit here. That's going to drive me nuts until I get an internet connection out there. I'm going to open up the C version here, and I'm going to compile it and download it right here. And just to kind of give you a feel for it, right here, when we do code in C, and we're not going to be using C in this semester, but I just want to kind of show you what happens here. You see where it stopped at watchdog timer control is equal to 0 DE. Over here, this is showing our code memory, and this is showing here that that command is translated to the assembly language command, move in the memory location 97 to number DE, right there. So the compiler translates the C to assembler for us. That's the job of the C compiler. So the C compiler takes our code that's written in C and uses the C command, watchdog timer control is equal to 0 DE. That's a C command. The assembly language command is move to memory location 97, and it finds the 97 because that's the watchdog timer control register in the include file. It knows that that's memory location 97, and it translates that to a move command right there. It sees this instruction here, port initialize. That's a function call in C, right? It translates that to a long call to an instruction right there. So if I single step through this and I call that function, notice that it goes to that instruction inside that function. So my debugging in C is really very similar. Only thing is I'm looking at the assembly over here. So this is the assembly command, pm mod is equal or equal 02. That is translated to a logical OR right there. So I see the assembly language commands for the C compiler. So even though I write in C, my debugging, my single step is done in there, and my next one is my return, and I go back to right here. So I can see, if I write in C, I still am debugging in the assembly language. That's why, as I mentioned before, we may not write in C, but when we start debugging, we quite often are looking at the assembly language that there to see what's going on in our registers, what's going that there. So writing in C is easier, but you're still right back to the assembly language code generated by the C compiler. That there. So the debugging process in C is very similar to the debugging process in assembly language. That there. But as you go through and you step through, you're seeing it go through all these various function calls right here. Right there. And again, I can still pull up the same windows right here, debug window, special function registers, right there. And I can look at, right here, timer control. Is that one of the ones here? No, it's not one of the ones there. But you see, I can pull up, view, debug windows, special function registers. Where are my there's my timers. See, and this shows what my timers are doing right there. So I can see everything that's going on, even when I'm in assembly C programming language. I still use the same tool right there. So with that said, I'm going to kind of wrap this up. It was a little bit shorter than normal, simply because I don't want to overwhelm you with too many examples of one that's there. When you do this in the lab, now, let's be honest, do some of these instructions make more sense seeing them done here now? What's actually happening as we go through this? Does this make more sense than it did yesterday? No one's answering. Hopefully it makes more sense. In other words, do you understand it better today than you did yesterday? Okay. That's what I'm trying to find out, whether or not seeing the examples, and then when you actually start doing it, it should make more sense. Yesterday, I threw a lot of instructions at you. I didn't expect you to realize, but as you see them being executed, that they're, so with that said, I will stop my recording. Oh, this was a short day today, less than an hour.